Good morning, dear students. Let us take up the next topic here, the steady magnetic field. This is a let's talk about steady magnetic field. At this point, we shall begin our study of magnetic field. At this point, we shall begin our study of magnetic field with a definition of magnetic field itself and show how it arises from a current distribution. The relation of the steady magnetic field to its source is more complicated than in the relation of electrostatic field to its source. So magnetic field can be originated by any one of these three things. That is, source of steady magnetic field may be a permanent magnet or an electric field changing linearly with time or a direct current. So these are all the three possibilities of getting a magnetic field. So we just concern ourselves here with a field produced by a differential DC current. Let us talk about biot-savart law here. Consider a differential current element as a vanishingly small section of a current carrying filamentary conductor. We assume a current I flowing in a differential vector length of a filament dl. Assume that here there is a filament. This is a filament. You have to consider here a very small length. We call it as a differential length. That is what we call it as DIL. We assume that the current I flowing in a differential vector length of the filament DL. The law Biot-Savart's law states that at any point P, the magnitude of magnetic field intensity produced by the differential element is proportional to the product of the current, the magnitude of the differential length, and the sine of the angle lying between the filament and a line connecting the filament to the point P at which the field is desired. Also, the magnitude of magnetic field intensity is inversely proportional to the square of the distance from the differential element to the point P. So we found that here the differential magnetic field at point P, which is equal to I, that is current carrying filament, for the differential length dl, and the distance between what we call it as the vector or distance between what we call it as from the field point to the current carrying filament we have. So AR here represent a unit vector in the direction of the distance between the current carrying filament and the point P. If this you are representing a distance vector R12, then AR is the unit vector in that direction. The sine theta angle here we have not taken. We have introduced here a cross symbol here. That means I have I into dl and I have a unit vector in the direction of this distance between the two, that is a field point and the line current carrying filament. So sine theta we have not used here. We have used a cross symbol here. That is vector I into dl into AR into sine theta. Instead, I can say that it is cross product of I dl into AR divided by, we know that it's inversely proportional to r square. That is, proportionality constant 4 pi we have. So it is 4 pi r square we have here. So in short, we can say that Biot-Savart law in an equation form, we can write it as a differential magnetic field experienced at a field point P. Just refer this figure. So at this point P, we found that the differential what we call it as differential magnetic field experienced at this field point is equal to I into dl cross AR divided by 4 pi r square. So this is about the Biot-Savart law. It is impossible to check experimentally the law of Biot-Savart as expressed previously because the differential current element cannot be isolated. Whereas, you can experience the integral form of Biot-Savart law, that is H is equal to integral of close line integral here, close line integral of I into dl cross AR divided by 4 pi r square. So this is what we call it as integral form of, biot law. That is, we are going to integrate to get the uh, total magnetic field experienced at point P. We can have here different sources. We can have different sources. Based on that, you will see that this can be changed. So we will see that we can say that I into dl is equal to k into ds. If instead of this current carrying filament, instead of it is a line conductor, if it is a surface, then k into ds we will be having, and in case of closed volume we will be having j into dv. So this is the change you will be getting as you change as you get the different sources here. So the source for the magnetic field at a field point P, we took it as the current carrying filament. Then it is I into dl. If it is a surface, then k into ds. And if it is a volume, it is j into dv. So this is about the biot law. Next, we can talk about Ampere circuit law. Ampere circuit law, it's very useful, in solving electrostatic problems. Whenever a high degree of symmetry is present, we found that they could be solved much more easily by using Gauss law compared to Coulomb's law. Again, an analogous procedure exists in magnetic field. The law that helps solving problems more easily is known as Ampere circuit law. The derivation of this law will wait until several we will be discussing that little later. For the present, we accept Ampere circuit law as another law capable of experimental proof. Ampere circuit law states that the line integral of magnetic field intensity H about any closed path is exactly equal to the direct current enclosed by the path. So I repeat, what is Ampere circuit law? Ampere circuit law says that the closed path integral of magnetic field intensity H is equal to the current enclosed. So we found that whenever there is a current carrying conductor exists, you will see that magnetic field will develop, around that. So if you are taking a closed path integral of that magnetic field, then that closed path integral should be equal to the current which is enclosed by that closed path. So this is what we call it as Ampere circuit law. This will be useful to solve problems, in the coming section. Thank you.